So in the introductory talk by Professor Saurabh, he started with committee, right? Remember? So this is what I'm going to talk about. So voting theory will capture this committee selection problem. Okay. And so we have 4 talks on voting theory, plus 1 is research direction in this domain. Okay. So 2 talks are by me and 2 are by Dr. Nimrod Telmon from Ben-Gurion University. Okay. So as Sushmita said, matching, which you just learned in the last lecture, falls in this category, collective decision making in the society, right? Because this is what we are doing, right? So now can you think of some examples, more examples in this domain, where you see collective decision making? Absolutely. Huh? Voting for a government? Exactly, right? So all of you are correct. So this is the most natural scenario which comes to our mind, that when we talk about collective decision making, which is political election, right? So what happens here? We all are voters actually. I'm pretty sure none of us is a candidate, right? So we all go to booths and vote for our favorite party, right? Yeah, because of our leading party, our winner is here is BJP, right? Okay. So any other application? So political, when we think about election, political election is natural to think of, right? What are the other application of elections? Yes? Fairness? Fairness is maybe a criteria we would like to have for election, right? But what are the other models that fits into this framework? Exactly. Very good. Very good. Yeah. Yeah. These days, actually, even to schedule the class, we circulate a Google form. To schedule a quiz, exam, we circulate Google forms, right? Those all are examples of your election, right? What else? More examples? Yes. Selection of job applicants? Absolutely. Right? So we can see that it's not just the political election, but we can see this problem actually everywhere around us, right? It's ubiquitous, right? And more examples. Page ranking, right? It ranks based on the keywords, based on the how frequently you search a website, and so on, right? Amazon, your product ranking, right? Committee and organization, all of you already said, right? How many of you are researchers here? Right? So you know selecting a research article, and how many of you reviewed the papers actually? I should ask this question. 1, 2. Okay, okay, very good. So you know, right? Whoever has reviewed the papers, you know that that is also like voting, election, right? Because we rank based on the multiple criteria, right? And that is aggregated later on, right? Okay. So movies in the plane, in a plane, right? Banquet menu, right? Because we also had this issue, how to choose the menu for your special dinner. And if, of course, a lot of conferences are going on at this time, right? Like algorithm conferences, right? And I don't know if you were aware, or if you were aware, then maybe you chose IT Jodhpur conference. So IT Jodhpur conference was winner in that case, right? Okay. So now we all understand what is the model, right? Now, okay, I know that we have voters, we have candidates, and I want to choose a winner. What are the points that we need to consider here, right? First point, how to cast vote, right? In our country, we just go and vote for a one person, right? But is that the only way? Correct. Exactly, right? So there are many ways to cast a vote, right? So largely, these are the well-studied methods: ballots, approval, ranking, and cumulative. Okay. So in approval, what happens that I just go and list this set of candidates that I like. Okay. So for example, in our country, we just go and rank for one person, right? One party. But why one? Right? Maybe I like BJP and Congress equally, right? So that is why you just so it's like binary thing. Either you approve or disapprove. Okay. Okay. So these are not drawn by me. I have this is drawn by Piotr Falsalski. I like these pictures, so I asked him to. I asked him for a permission if I can use these pictures. Okay. Now next is ranking. So what happens in ranking? As I said, right? You rank, maybe you do not have such a strict preference that you will either like or you either dislike or you completely dislike, right? But you would like to rank based on your preference. Okay. So you're ranking everybody, right? Based on your preference. So it's first, second, third, and so on. Okay. The third is cumulative. So here you split the percentage of your vote to the candidates. Okay. So your vote is 100%, of course. So you will say that, okay, I like this, I give 20 percentage to this green lady, 50 percentage to this blue guy, and 30% to this red guy. Okay. Okay. So in this school, mostly we will focus on ranking, right? And sometimes maybe approval, but most likely will not touch cumulative voting. Okay. Okay. So here, if you see there, you are strictly saying that this is my first, this is my second, right? But here it's not like that, right? I can say there's a difference between saying, okay, I give my 30% to this and 40% to this, rather saying this is my 20%, 50%. So this weightage you can see, right? You can convert this to a ranking. Very well, true. But opposite is not true, right? Okay. So now our formal model is as follows. You have voters, right? And you will rank every candidate, rank candidates based on their preferences. Okay. So I might use ranking as well as preferences, both meaning is same, right? And this complete thing, like this will be called, let's say, preference of voter V1. Okay. And this whole thing is called profile. Okay. Preference profile, we can say. Okay. And now goal here is to choose exactly one winner. Okay. There might be multiple goals, but for now we restrict ourselves to choosing one. Okay. So in the morning, like he's talked about the committee. So you can think that committee size is here 1. Okay. Okay. So next point which we need to consider is how to choose winner. Right. So you have votes, right? You specified how to vote. Now you have votes and you want to choose a winner. How to choose? So now you can think of anything like you may call it a method, you may call it a voting rule, you may call it an algorithm, whatever you want to call, you call, right? But this is a method that given a set of votes, how do you choose winner? Okay. Next question to you. What are the possible voting rules that you can think of? Yes. Throughout the talk, I will talk about a strict. Yes. What are the possible voting rules? But rule. Given the rankings, how do I choose my winner? Yes, this is one method. First preferred. Exactly, that is one possible voting rule. Yes. I'm not talking about good or bad. Just say. Okay. There's no voting rule which, I mean, this is serious thing. There's no voting rule which you can say that, oh, this is my best voting rule. I can apply it everywhere. There's no such voting rule. Okay. So just feel free to say your voting rule. So how do you define incentive? Depends on candidates, right? And based on the incentives, maybe you would like to rank them, right? But now you have submitted your vote, right? Yes. Okay. Mm-hmm. Mm-hmm. Correct. Yes. This is one possibility, right? And actually, whatever you guys said, we will discuss those things only. Okay. Okay. So let's first ask ourselves, like you did not consider the number of candidates so far. Like whatever rules you were saying, you did not consider that, right? What about when you just have two candidates? Can we do something nice, better? Exactly, right? Two is not a big deal, right? Two is not a big deal. You can just apply your majority rule, right? You see, oh, you just have two candidates, see whoever is most preferred, right? And just that person is the winner. And it is actually theoretically proven that for two candidates, this is a good rule. Okay, when I say good rule, in this school, we are not going to talk about the axiomatic analysis, but there are some axioms, right, based on which you can say that your rule, if your rule satisfies a lot of those properties, meaning it is acceptable. Okay, but this is more about algorithms, so we'll not talk about axioms. Yeah. Mhm. Very good point. What if there is a tie? This is exactly a question, right? What if there is a tie? Because I have the odd number of voters here, so the tie is not possible, right? But she's absolutely right. What if even number of voters we may have ties, right? So actually, voting rules come with the some tie breaking rule. Okay, so you will break ties accordingly, right? It could be anything. It could be, for example, you can ties in lexicographic order, maybe, right? And there could be any other ways as well. Okay. Okay. So let's talk about the case when we have more than two candidates. Okay. So the first rule, which is widely used, right, in India as well, plurality rule. Okay. So what happens here? I think he was saying that look at the candidate, right, who is at the like who is uh, yeah, who is at the first place maximum number of times, right? So for example, if you look at this green lady, right, she's at for two voters, she's ranked one, right? If you look at this blue guy, only one voter ranked him at the first place, right? This one, right? So this green lady is the winner under this particular rule. Okay. Okay. Next question to you. Any problem with the plurality rule that you see? Yeah, that is again tie break, tie, right? Ties case. So you will break tie based on your tie breaking rule. Again, that's story same. Haha. Correct. So maybe he is more desirable, right? So what he is saying, yeah, you have any question, anybody here? Okay. So what he's saying that plurality rule is simple, fine, but it's not, it doesn't look very good because look at our winner. Okay. She's our winner, right? But look at V3 and V4. V3 and V4 are quite unhappy with this candidate, right? So that is a problem with this plurality rule. So if you ignore this red guy, right? If you just look at this green lady and this blue guy, right? As he said that he looks like at least more desirable candidate, right? So that's the problem with plurality rule. But still it is used very frequently, right? In most of the countries, plurality rule is used. The main reason is that it is very simple to apply. People understand it very well, right? And it is applied since ages, so people think that maybe it's a good rule. That's why everybody is using historically, right? So maybe that's the main reason that it is used. Okay. Okay. So the problem here, why do we have this problem? Because we just focus on the first ranking, right? There's a point of giving the ranking here. If you don't care about the ranking, right? Why do approval is the same as that, right? So exactly, right? One approval, just approve one candidate, right? So this is the problem here. Okay, it is actually not using your ranking. It is just ignoring whatever comes after second position, right? Okay. So next rule that we are going to talk about is the Copeland rule. So again, on purpose, I have three candidates here, three voters here. So we do have pair-wise comparison here. Okay. So what we will do, we will draw a graph. Okay. So for every candidate, you have a vertex. Correct. Now let's compare the, let's do pair-wise comparison between the candidates. Okay. So let's say if I compare this, these two candidates, right? Then what do you see? Who is the most desirable person? Right? So I can say that majority of the times, right, she beats this blue guy, right? So you just add this arc. This arc tells you that this, you can say this head and tail, whatever you want to call. So this green lady beats this blue guy, okay? And we will do this for every pair of candidates, okay? So now let's compare this green lady and red guy, right? Now again, you see that she beats this red guy, okay? So again, I draw this arc, right? Now, if you look at this blue guy and red guy, right? Then what do you see? This blue guy is more preferred than red guy, right? Because he is preferred by 2 voters, and he's red guy is no. Actually, for all the voters, blue guy is preferred. Okay, so I add this arc. Okay, okay. Now, given this, I think it's simple in terms of thinking in terms of the graphs. That's why I've drawn the graph. You can do without graph as well. Okay. Now, for every candidate, we will find the Copeland score. Okay. Yeah, Copeland score. Actually, for the other rule also, you can think about plurality score, right? Look at for everyone. Look at the voters who ranked him or her first. That is the plurality score of that particular candidate. Okay. Now, what is the Copeland score? Look at the number of outgoing arcs. Okay, minus number of incoming arcs. Minus. Okay. So total number of outgoing arcs minus total number of incoming arcs. That gives you the Copeland score. Okay. So what does it signify? Outgoing arc. Number of candidate he beats. Right. And what does this incoming arc denote? That number. Correct. Correct. Defeated by. Right. Okay. So that margin is basically your Copeland score. Okay. Victory margin is your Copeland score. Okay. So for this blue guy, 1 outgoing arc, 1 incoming arc, 0. For this green lady, 2 outgoing arcs, no incoming arcs, 2. For this red, -2. Very good. Okay. Yes. Yeah. So, okay, I'll not go back. I'll just explain you here. We will do pairwise comparison. Pairwise comparison. Okay. So let's suppose we want to compare this and this. Exactly. Huh. Yeah. Yeah. Okay. I think yes. Yeah. It's a name. Okay. You don't add arc. Add arc. Okay. That's I have that example as well. Okay. Okay. So is that clear? Score? Yeah. Okay. So can it be same meaning for two candidates? It can happen. Number of incoming arc, number of outgoing arc can be same, right? For different candidates. Come again? King in a tournament. King. What is the definition of your king? Source. Maximum degree. Maximum out degree. Okay. Need not be. Okay. So again, if we have 4, right? So it's the same example. Okay. So now let's again draw this graph. If you compare this blue and green, right? Then what do you know? 2 voters prefer this green lady over this blue guy, right? And 2 voters prefer this blue guy over this green lady. So there's a tie. You will not add anything. Okay. Similarly, if you compare this green lady and this red guy, again the situation is same. 2 voters like her over this red guy and 2 voters like this red guy over this green lady, right? So you'll again not add any R. Okay. Now let's compare this blue and red. Okay. So blue is preferred over red by 3 voters, right? And V4, like just 1 voter prefer this red guy over this blue guy, right? So you will add R from this to this. Okay. Now again, the method of computing the covalent score is same, right? Yeah. Huh. So number of outgoing arcs minus number of incoming arcs, right? So for this blue guy, what is the score? For this green lady? For this red guy? Very good, right? Okay. So covalent score actually ignores your ties, right? In this figure, you can see that, right? But there is also something called alpha covalent score, right? Which gives alpha weightage to the ties. Okay. It's not 1 weightage, it is alpha weightage, which is something less than 1. Okay. And that will be considered here, but I'm not discussing that. I'm just telling you there is something called alpha covalent, which also consider, which also gives some weightage to this, right? And which is reasonable because, see, you're complete. This is not bad situation, right? Right? She's not defeating, but she's also not beaten by someone, right? So this is not a bad condition situation, which we are completely ignoring, which is considered in your alpha covalent score. Okay. Yeah, this is the winner. Next question to you. King is the winner, right? King is the winner. Oh no, because he said that a number of outgoing arcs is large, but right. But for the same person, number of incoming arcs might also be large, right? Mm-hmm. Oh, he's not beaten by anybody? I see. It's like a source then. No incoming arc? No, just tell me what is your definition of king? Even if everyone is defeated by other indirect. Okay, let me draw this. Then we can do this. Okay, I cannot draw these figures, so let's have these points. Okay, with the same color. Once again. This is green. This is my blue. Okay, and this is my red person, winner person, right? Now tell me, what is king? Any tournament? Okay, let's see this. Okay, and correct. And what if I draw this? Everybody is what? So the king either beats somebody directly or beats someone by just one move. Okay. So you mean king? So you mean to say that for king? I see. Wait. So you mean that king is a person who beats? What do you mean by one hop? If I delete this arc, then that is the one hop. What do you mean by hop here? I don't understand. Hmm? Two-degree path, two-length path. Okay, but if there's a two-length path, okay, then it's like this, and for you can say that there's no direct like arc from this blue to green, right? But it is through this thing, red, and that is why it is a wing. Okay, fine. But still, I don't know. I don't think that your king has to be winner, right? Because it depends the number of outgoing and incoming as well, right? Come again. Based on the covalent score, highest covalent score. Tie rule. Tie breaking rule. Unless you have a covalent. What do you mean? What is the problem with cycle? You have a cycle, right? I can have something more, right? Still, you can come up with, right? You will always find some covalent score, right? Because covalent score does not care about being cycle, non-cycle, right? It just depends on the number of outgoing arcs, number of incoming arcs, right? So you will have some covalent score, right? Whoever has largest covalent score is your winner, right? If there are multiple candidates with the same score, then you will apply your tie breaking rule. Okay? Yes. See, this graph is always going to be a tournament, right? This graph, yeah, so this graph is always going to be tournament. I don't think there's any relation between king and covalent. Of course, we can talk about it later and discuss more, but I don't think there is any relation, okay? I think we can easily come up with some counter example. Of course, this is what I said, right? You can also do without graph, right? Because what is it doing? It is just saying that look at the pair, right? Look at the number of voters who look at, like, you know, you understand, right? Sorry? No, that's a different rule. That's a different rule. Because here you are doing pairwise comparison and you are counting the number of votes. Like, let's say you have this green and blue, right? Then you're saying, okay, for how many voters this green is more preferred than blue? For how many voters this blue is preferred more than green? So this pairwise comparison is different than this you are giving ranks. And we will come to that score also. Next rule is that. But it is not just about one, right? Okay, suppose I give, okay, you want to give 0, 1, 2, right? Suppose you want to give that. Then what should I do? That's a different rule. And you can check that's a different thing. It's not going to be same. Yes, this is exactly. You can think about that, right? Because it's like in majority rule, right? You had just two candidates and you compare them, right? Now what are you doing here? You have more than two candidates, right? So you're trying to say that, okay, now if I do pairwise comparison, then what is happening? Right? If I restrict myself to just those candidates, then what is happening? And I do this for every pair. Okay? So this is what is happening. I'll come to your score and that's a different rule. Okay? It is not possible. This such a graph is not possible. No, I'm sure that is possible. No, for this particular election, it is not possible, but you can come up with some other election for which it is possible. Okay. Right. What is necessary? No, it's not. In this rule, it's not. Okay. 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 Hold on. Now, what is the problem with Copeland score? Time, yes, time is one constraint because you are doing it for every pair of candidates, right? But what else other than time? Suppose I give you time. Uh, V1, V2 is are candidates. Okay. Compared with whom? You mean compared with other candidates? Uh-huh. V2 won, but under which rule? Fine. But V1 we declared because V1 got the more yes, right? No, V2 is better than V1 by most of the candidates. Okay. Let's see if we okay. Yes. Yeah, but when can it happen? Like, what is the situation when it can happen? Hmm? Yes, but blue is was more desirable also in some sense, right? Right? Let me draw. Uh, okay. Say it. Green to whom? Should I draw 3 more vertices? Okay. No, but you need to see, right? Because it is going to be tournament. So what is happening with respect to this green and this newly added vertices? That's what I'm saying. It's not a tournament yet. It has to be tournament. It will always be a tournament, right? Are you saying this? Oh, okay. Okay. Yes. Okay. Okay, yeah, that may that may happen, right? Green beats, right? But that may happen. That's fine. Okay. Okay. But what are the other things? Other thing is that when you are doing this pairwise comparison, right? You are basically ignoring this margin of victory, right? What you are saying that it is just +1 -1. You beat, you are beaten by. You just cancel out this effect, right? So you're just ignoring this what you call margin, right? Exactly, right? So that's a problem with Copeland. And now I'll come to the rule which he was saying. He was trying to merge with Copeland rule. There's a Boda rule, and again, this rule was given by Boda. Before you ask why the name is Boda, okay? So in this, you give points, right? In the sense that look at the last ranked candidates, okay? All of them are getting 0, right? Then 1 and 2. Okay, so basically you can think that look at the number of candidates, which is 3 here, right? Subtract the position of this candidate from the total number of candidates, right? So position is 1, right? So this is 3 minus 1, 2, 3 minus 2, 1, 3 minus 3, 0. Okay, and this is called Boda scores. Okay, don't call this Boda score. I'll call something else as Boda score. Okay, so for the every candidate, right? Now we will compute the Boda score. Okay, so Boda score is what? Simple, right? Just sum up. Okay, so look at no, just forget about this. Look at this green lady, right? Look at 2, 2, 4, 0, 0, right? So 4, right? Look at this blue guy. 1, 1, 2, 4, and for this red 0, 0, 1 plus 2, 3, right? Okay, so winner is blue. Okay, so you can see there is similarity between all the rules which I just now said. Okay, the first thing is they are trying to see whoever is most preferred person, right? Using some way, but that is the main idea, right? That it is trying to capture. Now, who is most preferred? That is what we are trying to capture using different rules, correct? But that is the bottom line, that is the broad idea rather, that look at the candidate who is most preferred, and that is what we are trying to capture. Okay. Okay. No, there's no relation, but that's what I'm saying that in Copeland also what you were trying to say, I do pairwise comparison and who is the most preferred, right? And then whoever is got the highest score is the winner. Plurality also I did the same, highest score. Boda also I did the same thing, right? Okay. And you can see that all these things are polynomial time computer. Okay. And of course, in real life, I want to choose a winner. I would like to have such thing, right? In polynomial also, I would not like to have n to the power 1 million type algorithm. It needs to be simple. It needs to be easy to compute, easily computable. It should be easy to understand as well. Otherwise, society will not accept it. If you go and tell, if you reveal your rule, right? Okay. Yes. Huh? Mhm. So that is not Boda rule. Yeah, you can think about something else, right? So that one can we think like what is that called? Okay, so there's some name weighted. You can think, right? Right. So that is fine, right? So instead of that, what will you? Rest of the rule will be same. Okay. So you can say that. scenarios, maybe the reverse is better, right? Yes, you have any question? What? Come again? Fraction, yes, you will get. Yes, of course, all these things can be done. Okay, you can come up with all these things. And in my next lecture, when we talk about the multi-winner voting, I will tell you that you can have actually many things there. And like there's a common theme, I would say, that you can, no matter what you define, there is a way to aggregate everything. Okay, so we'll talk about those things tomorrow. Okay. Okay. So these three rules are clear, right? Okay. So now the next sort of voting rules which I'm going to talk about is that why always think about that, okay, I will choose the like best one, right? Like why this should be my approach. Someone I think said this thing that whoever is, less desirable, let's first him or her. Yeah, you said, okay. Okay, so and what happens that nobody's vote also get wasted, right? Maybe the one is less desirable if you look at the overall ranking, right? But if I look at for sample, maybe that is the person who's most preferred, right? So that's will be quite unhappy, right? But what you would like to do is transfer his vote, his or her vote. Okay, so next set of rules are based on that idea. Okay, so plurality runoffs. Okay, so what we do here, we check if there is a candidate ranked first by the majority. Okay, so by majority we mean 50% of votes, at least. I mean more than 50% of votes. Okay, so if that is the case, then that person is the winner. Okay, if that is not the case, yes. Mm-hmm. What do you mean by wrong? Yes. Uh-huh. Uh-huh. Yes. Winner may change. Who said this should be the winner? Winner is based on what is your voting rule, right? And voting rule is based on what is your application, right? We are not saying that this is the best voting rule and you should always use it. No, we are not saying that. Okay? Okay? Okay. So in plurality runoff, yeah, you first check if there is a candidate ranked first by more than 50% of the voters. Okay? If that is the case, winner. Otherwise, you just focus on two candidates with high plurality score and apply your majority rule. Okay? With two, I know how to apply majority rule. Okay, let's look at the example, don't worry. Okay, so here I have changed input a bit on purpose. So by 4, I mean there are 4 voters, right, with this particular ranking. There are 2 voters with this particular ranking. There are 5 voters with this particular ranking. There are 3 voters with this particular ranking. Okay. Okay. Now, what is the plurality score of 6? Okay. So her plurality score is 6, right? What is the plurality score of this blue guy? 5. Red? 3. Okay. Now, based on my rule, what should I do? What is the total? 14, right? So what should I do? Exactly. So my first right? That answer is no. Right? So I did not find the winner. Now what will I do? I will look at the yeah. So majority, right? So let's just focus on these two. Okay. Now what is the plurality score? Like now you apply this, not plurality. Now you apply your majority. Right? So who's the winner? Right? If you apply your majority, right, then for this green lady, right, she is more preferred than this blue guy by 6, right? And he is preferred more than this green lady by 8. So who is the winner? Okay, clear? Okay. So yeah, I mean this is simple. I don't have example for this. So in this, you just drop the candidates with lower score. Okay, compute again, right? So whoever is eliminated at the end is your winner, right? Okay. Okay. The next rule is STB. STB is also actually used in many countries for the political elections. Okay. So what you do here, you delete the candidate with lowest plurality score. Okay. And then the vote is transferred. Okay. What do we mean by that? Yeah. You mean how to transfer the vote? Yeah, we'll look at the example. Okay. Okay. So okay. So the plurality score this red guy is least. Okay. So we will delete him. Okay. Okay. Now scoring lady. See, what do I mean by transfer the vote? For this particular now, he is at the top. Okay. Anywhere, but for this part, these 3 voters, top is this now. Okay. So what is the plurality score of this? 6. But what is the plurality score of? So he's the winner. Yeah, you can. This is because I have 3 candidates here, so you can think that okay, in this particular step, you will drop a green lady, and then at the end, blue is the winner. Yeah, it is iterative. Okay, so you keep applying, and whoever is eliminated, then the winner. Okay. Now, eliminating based on your border score. Here you are eliminating based on your no, no. That will be highly undesirable. We need to conduct the election again and again. Nobody will go and vote. Yeah, but how will you convince voters to vote, let's say, M times? Because at a time you will just eliminate one candidate, right? So nobody will go and vote. So far we were talking about that you have voters, you have candidates, and you want to choose one winner, right? What are the elections? Correct. I'll talk about it tomorrow. What else? Yeah, that's what he said. Committee. What else? What do you mean by that? Yeah, so then in some sense that there you are choosing single winner. Yeah. No, what do you mean first prefer? Whoever had highest score. Mm-hmm. Okay. Okay. Mhm. So you're saying that instead the could be single winner still, right? But instead of one winner, you choose two, and one person is like backup plan, right? Yeah, right. Okay, fine. So other than this choosing one person, two person, five person, there's also something called aggregated ranking. Okay, so we our input is also ranking, so our output is also ranking now. But in input, you have uh, ranking for each voter, and as output, you have one ranking. Okay, that is what I mean by aggregated ranking. Yes, you want to say something? You are saying something? Okay. Yes. This setup. The- Yeah, yeah. So how to do it? That we will discuss later. But is my input? Input is still same, right? You have voters, and every voter rank candidate based on their preferences, right? And the outcome is ranking. Okay. And again, how will you choose? Based on some rule, right? Some method, some rule, but this is a commonly used terminology. Okay. Okay. Is it used? Recommendation system, and actually all these examples are for recommendation, right? Okay, so this is I mean my rank aggregation, right? Because you had a lot of rankings, right? And you aggregate them somehow, right? And get a particular ranking. Now if you imagine whatever rules I discussed so far, based on that, can you get a ranking? It's not possible. Based on the scores, right? Right? Yeah, and again, you can break the ties arbitrarily or using your some tie breaking rules. Correct? Okay. And there is also a specific rule for not just one, there are many more rules. We will talk about this is the most famous rule, Kamini rule. Okay, and this is for for rank aggregation. Get rank, right? Who is that? Right. Okay. Now, so this measure distance between two rankings. Okay, and find this distance now. Okay, so this is defined using this as a name because this is nothing specific to your what you call it, right? This you can use for measuring the distance between any permutations. Okay, this is basically permutation, right? Okay, so we lump candidates which they disagree. Okay, so for example, this kings, right? Disagree, right? Okay, and for what's what mean by disagreement? Okay, so okay, number okay, zero or one only. For this pair, empty. Okay, for this particular pair, again disagreement, right? So what distance summation of these values. Okay, now it's clear this definition. Come to the number, right? This is disagree. Always they disagree. Okay. Okay. So now in Kamini's rule, the ranking, right? Of course, ranking on these particular candidates only. Ranking such that distance between VI is a motor, right? Distance, distance, right? So right? Dialyzed. Okay. Okay. So look at an example. Okay. I hope you can see this goal. Is it visible? Okay. It's the same. I mean, yeah, but in case you do not remember this, I have written. I cannot draw again, use this thing. Let's say, okay, what? Tell me. Tell me one ranking. Say anything. Come on. Blue, green, red. Okay. Okay. So this is my pi. Okay. Unlike this is the optimal solution. Okay. But let's see, given this will be your Camney's score. Okay. Okay. So let's go. Okay. Tell me V1 and pi. I will not compute. You will compute. What is the distance? One. I will believe you whatever you say. 5. How many of you say 1? I'll see if the majority says 1. I'll write 1. Okay, let me write 1. Distance between V2 and pi. Oh, right. What is the distance between V3 and pi? 1? Okay. What is the distance between V4 and pi? 2. Okay, 2. Agreement or any disagreement? Okay. 100% agreement. So what I can is score? 5. Oh, you don't have Kemley's score. Okay. Yeah. So this is the Kemley score, 5. Okay. Okay. But the bad news is design polynomial time algorithm problem. Okay. But that's a good question. Because we can give a redundant feedback set in tournament problem to this problem, and feedback arc set tournament problem is known to be NP-hard. Arc set in tournament. I'll discuss that definition. Don't worry. Yeah, the number of inversions. Yes. Yes. Okay, then maybe it's not counting inversions, just it's something more. But yeah, it is known that it is a NP-hard problem. Like there is no polynomial. We cannot hope to design polynomial time algorithm problem. Okay. Okay. And the rule is very strict that even for 4, you cannot hope to design polynomial time algorithm. Okay. Ranking. Yes. Correct. No. You have to come up with a ranking. You're right. You have to find a ranking which minimizes the sum. That's the issue. Yeah, you're right. Okay. So for 4 voters, it was proved in 2001. Okay. But what happens for the odd number of voters? Then odd number of voters is constant. Odd number is constant, right? It was open for a long time. And in 2019, it was proved that even for odd 7 voters, this problem, yeah, we cannot hope to design polynomial time algorithm. I don't want to use NP hardware today because you're not. When we can have algorithm? Yeah, this is about, right? Oh, no, matrix. I don't remember. Yeah, but we can look at that paper, right? Of course, it cannot be constant, right? Because the reduction is from feedback arc set problem and the vertices are mapped to the candidates, right? So it cannot be constant for sure, right? Now we need to check for what, what is, if there is something known for the feedback arc set problem. It will depend on that. I mean, that's a rule, given is rule. I don't know if product is even studied. Okay. And product has many more challenges itself because, it grows exponentially anyway, right? So, but yeah, it can be converted to summation things and a lot of those things. But yeah, it itself has a lot of challenges. Okay. So, so in 2019, it was proved that for 7 voters also, yeah, we cannot hope to design polynomial time algorithm. Okay. And okay, now the yeah, these are the papers. Okay, this is a 2001 paper, right, which has this 4 voter thing, and this is the 2019 paper, which has the hardness for 7 voters. Come again? So how many permutations are there? Given a profile, permutations are there which attains the least fit score. Like are these kind of profiles? I don't want to find one. I just want to say there are 5 of them. Which fit? I don't know which one. Can we say something? I don't think such things are studied. You are saying that you just want to come up with the count that there are 5 rankings. But you will not find them. Yeah. I don't think such things are studied, but I think yeah, it would be interesting. Yeah. Oh, because of this odd and even thing. Odd and even thing. Odd and even. Yeah. No, for 4 it is known it is hard. It was already known to be hard, right? For 5, I don't know what is the status. Okay. Yes, this is exactly what she's trying to ask, right? In hardness, right? When we say it is hard for 4, it doesn't mean it is hard for all the values, right? And especially maybe your reduction can be easily generalized to other things. That's a different thing, right? But here the bottleneck is for like all. Maybe the reduction doesn't work for 5, right? There are technical challenges, right? Okay. So I'll this reduction that shows that you cannot admit polynomial time algorithm, right? But I will tell you that this problem for all number of voters can also be reduced to arc-set problem. Okay, it's not a one-way reduction, but it is like two-way reduction. Yes. Page strength? Yes, this is exactly what we are saying, right? Yeah. So let's look at this reduction. Okay, I think I have enough time to discuss this. Okay. Okay, how many of you know feedback arc set problem? Okay, let me say the definition. Okay, let's go slowly. Feedback arc set, right? So as an input, you are given a directed graph G right? And I'll talk about the decision version of the problem. So a directed graph G and an integer K. Okay. And my question is, does there exist a set S, basically a subset, right, of the edges such that G minus S does not have any direct cycle? Okay. Yes. Of size at most K. Okay. Of course, otherwise the problem is trivial. You can delete everything. Right? Okay. So, do you understand the meaning of G minus S? Right? You basically delete these arcs. Okay. Okay. Now, let's say what is weighted version. I mean, when I say weighted, it could be vertex, it could be edges, right? But I'm talking about a directed graph G with weights on edges. Okay. Does there exist a set S of, sorry, I don't want to delete. Weight. Okay. That's all. Okay. So there's also an equivalent definition of this problem which I want to use. Can you model this problem as a ordering problem? Yeah, ordering problem. Ordering. I want to come up with an ordering of vertices with some property which captures this problem. Huh? It's not objective. What is my objective? Suppose there is a directed cycle, so what do I do? There should be an ordering of what kind? Of vertices which captures what? No. Yeah, okay. There is a topological ordering, but in G minus S. Right? Yes, right? So let me add a page. So all of you are right that in G minus S, we do not have a cycle. So I know this is a property of directed cyclic graphs that I can come up with a topological ordering, right? How many of you know what is topological ordering? Okay, so everybody, since everybody doesn't know what is a topological ordering, meaning that you can come up with an ordering sigma, right, of vertices, right, such that if there is an arc, right, then okay, so let's say UV belongs to EG, right, then sigma U is less than sigma V. Okay, so we can say that all the arcs forward arcs. Okay, there is no backward arc. Okay, we can call this as forward arc and this as backward arc. Okay, and there's no backward arc. Okay, okay. So if I want to, I want to forget about this deletion problem. From the scratch, I want to write it as an ordering problem. Okay, so the question is very simple, right? Because what do you want to do? You want to come up not with topological ordering because this has cycle, so you might not have a topological. I mean, you will not have a topological ordering, right? So What will you do? You want to come up with an ordering of vertices such that the number of backward arc is minimum, right? So if I talk about feedback arc set problem, you want to come up with an ordering with minimum number of backward arcs. Do I need to write? Is it clear? Yeah. This is? Yes, this feedback arc set problem is already known to be hard, right? Even for unweighted case. This is known to be NP hard, and I didn't do anything. I'm just giving you a alternative definition, and both of them are equivalent. That's all I'm telling you. Okay. Okay. So in case of weights, right? The question is still the same, right? What do you want? You want to come up with an ordering of vertices such that the weight of the backward arc is minimum. Correct? And if I talk about the decision, then what do we want? Number of backward arc is at most k, number of weight of the total weight of the backward arcs is at most k. Okay. So the definition is clear to everybody? Very good. Now let's look at what is semi-complete. What did I use? Semi-complete diagrams. What is this class of graph? Do you know what tournament? Yes? Do you know what tournament graph? Right? Between every pair of vertices, these are your vertices. Between every pair, you have exactly one arc, right? But when I talk about semi-complete diagram, between every pair, you have at least one arc. Okay? So it means such arcs are allowed. You can have arcs in both directions. Okay? Okay. Now, the claim is this Kameni's problem you can reduce to weighted feedback arc set in semi-complete diagrams. So between every pair of vertices, you have at least one arc, right? So you have to have arc in both the directions, right? All diagrams? No, no. Every diagram is not same because in every diagram you might not even have arc, right? We are saying at least one. Exactly. Yes, you can have more edges, right? It's not like you will have, but you may have at least one. Okay. Okay. So this is something more than tournament. Yeah. Semi-complete. Yes. Something. Tournament plus something. Yes. Okay. Nice. Okay. So yeah, you can you think of reduction? Reduction from Kameni's. I want to give reduction from Kameni's rule to feedback arc set in semi-complete diagrams. Yeah. Feedback arc set. Okay, I'll write the full. No, this will not give you NP hardness. What did you ask? Yes. Yes, I'm not proving NP hardness. Yeah. Yes. Is it? Okay, fine, whatever. What is the spelling? K-E-M-E-N-Y?
It's Kemen, but then we moved to the United States, and in the United States, it would be Kemeni.
Okay, okay, okay. Yeah, yeah, reduction.
Feedback offset, yeah,
So feedback offset is this problem.
the permutation of vertices.
Yes.
Am I
Number, okay. Not just this, sorry. Weighted.
all weights are one. So all arcs are equal. No, there is a distance. It's weighted by distance.
Weight is on edges, right? Feedback offset. So weighted feedback offset meaning you have a directed graph and weight with weights on the edges, right? Absolutely. Yeah. So you have okay. So you have profile here. Okay. Okay. And for every candidate, okay, we had candidates. Let's say green, red, green, blue, right? So for every candidate, you will have a plus, right? Now look at a pair of candidates, right? Look at the number of voters, right? Let's say this is my what do you call? Let's say this is my red person, and let's say this is my green person. Okay. Look at the number of voters, right? Uh, for whom this is more preferred than green, right? Put that count here. Okay. So this is number of voters who prefer red more than green, right? Okay. So now you see we can have arcs in both the directions, right? You will not zero weight arcs. Okay. Zero weight arcs. You will not add, right? By which I mean that if nobody like red more than green, then I will not add this arc. Okay. Do you see the correctness? Think. So this is my gadget. Okay. So this is my graph G. Yeah. And let's say, let's say I was looking for Camry's score, let's say alpha, right? So here I'm looking for at most alpha backward arcs. Reduction is clear to everybody? Think. If you create two candidates, you will have arc at least in one direction. Right. But what does semi-complete diagram says? It doesn't say that you will have in both. It just say that at least one. So it allows you to have arcs in both directions. That's all. Okay. No, but I'm talking about odd number of voters. That's important, right? That is why I'm talking about the odd number of voters. Okay. Otherwise, also you will have some digraph, right? But what do you think? Why am I doing this reduction? No. No. Why this reduction? Tell me this thing. Oh, that's why I mean that's a part of equivalence, right? exactly their equivalence, right? This is exactly what I'm trying to tell you. Yes, exactly, right? Because this the weight on the backward basically tells you what is the disagreement. This is not my question. The question was, why doing this? Exactly. This will not tell me that this problem is difficult, right? Right? When I reduce this to this, right? Maybe a lot of problems I will be able to use, right? This problem itself is well studied, right? So whatever is known for this, not this is exactly what we are doing this reduction. Mhm. Yeah. Correct. I mean, so now how many number of backgrounds can you have? M square, yes. But because it's weighted, it can also be M square N. Go ahead. Yeah. Family score, but I don't know. If this value is given to you, right? Then in general, we cannot find in polynomial time, right? Huh? You mean yes or no? Yes. At least this much. Okay. Um, so one thing is, existing, it's just ends by m minus 1, nothing fancy, right? But I don't know if something is known. Ah, yeah, I understand your question, but I don't think this is something. Could be. Maybe I'll tell you tomorrow. I'll check this. Correct. No, but you can come up, yes, indeed, n square, but you can come up with a ranking with the score n square m minus 1. Yeah. So is the reduction clear, everybody? Yeah, because what you can do, let me make one more page. So what is happening here? Look at the, let's say this is my Camni ranking, right? With the sum on score alpha, right? What does it mean? Now let's look at the, I'm saying that whatever is this ranking, let's look at the same ranking for your feedback answer in tournaments problem. Okay. So alpha basically tells you, right? Alpha means that for this particular pair, maybe whatever was the disagreement. For this particular pair, what is the disagreement, right? And do you have disagreement? Because, okay, let's give some names. Let's say C1, C2, C3, C4. Okay, C1, C2, C3, C4. Okay. Okay, so if this particular pair, let's say C1, C2 is contributing in your alpha score, right? It means there are some voters for whom it is opposite, C2, C1, right? So then what it means? You will have this backward arc, right? So whatever is the contribution of this pair C1, C2 disagreement in alpha, right? That is exactly the weight of this arc. Agree? So forward direction is clear. Whatever is the Kemeny score here is going to be the number of gate or backward arcs, right? You look confused. You are confused? No, so it's okay. You ask. Okay, but I'm not using any theorem here actually. I'm not using any theorem. Okay, so let me say it again. I can take 5 minutes of your high tea break maybe. Okay, so what am I saying? Did you understand this? Did you understand this reduction? No, that is a definition. But this, did you understand the construction of G? Graph G. So construct graph G. Let me say it again. If you don't understand the construction, then you will not understand the proof. Okay. So for every candidate, right, we have a vertex. Okay. For every candidate, there is a vertex in G. Okay. Okay. Now let's look at this pair of vertices. Okay. You will add arc. Okay. When will you add arc? If there is at least one voter who likes red more than green. Okay. Then you will add arc. And what will be the weight of this arc? Number of voters who prefer red more than green. That's the construction. That's all. Okay. Now, suppose you are looking for a ranking with Kemeny score alpha. Okay. So here you are looking for a permutation, right, with backwards, right? It's like weight of the backward arc should be at most alpha. Okay. This is also at most, in case I said at least. Okay. So this is, everything is at most here. Yeah. So let's look at the, okay. Yeah. Okay. I'll come to that. Next, I mean, this is the previous page. I'll come to that page later. Okay. So let's say this is my Kemeny ranking. Okay. So here I will be talking about Kemeny, and here I will be talking about feedback arc set. Okay. Okay. So this is your Kemeny ranking, right? Okay. Let's say, of course, let's say its score is alpha. Okay. Okay. Now you recall your definition of Kemeny. Okay. Right. Suppose this pair of candidates, right, attribute something in alpha. What does it mean? Disagreement for at least some voters. Okay. And what is that? Whatever is the count of those voters, right? That count you have counted here. Right? Okay. Because there are disagreements, right? You will have this edge. Right? And what will be the weight of this edge? The number of voters. Right? And that is exactly the value that you counted here. Right? So whatever is the alpha here, that will be the weight of. Agree? This is exactly the forward direction proof. Okay. So in the backward direction, it's the same thing. Okay. So now you look at this feedback arc set solution. Okay. Okay, I don't know if you know how to prove the correctness, but this is what we mean by correctness, that when you construct these instances, you will prove that this is a yes instance of the problem, if and only if this is a yes instance. Okay. Okay. So now you have, let's say, a solution of feedback arc set. Okay. Now I'm saying that this exactly is your, and let's say the value here is alpha. Okay. This exactly is the ranking. Written this as a your ranking with Camden's score alpha. Do you think this is true, right? Because what count here? You will count the number of disagreements, and that is captured by your backward edge. That's all. Okay. Okay. So I told you all this story because feedback asked in tournaments is a very well studied problem, and most of the algorithms that are known for tournaments, right, also works for semi-complete digraphs. Okay, there's nothing like specific literature for semi-complete. Yeah, whatever is known for tournament, most of the things work for semi-complete digraphs. Okay, so you don't know these terms. I don't know if you know these terminologies, but you will learn at least during this school. This, fast, interesting name because this fast is for feedback asked in tournaments, and this is the faster algorithm, right? Fast local search. Okay. And there's also something known in the approximation word. This was a SORA 2020 paper, I guess. Yeah. So that's all. Okay. That is why I told you this reduction. Okay. Thank you. If you have any questions, you can ask. Tomorrow we will do in voting. I mean, we'll do many things, but in voting theory, we will do this multi-winner election, committee selection problem. Yeah. Your question? Yeah. You asking for application? You're asking for application? Huh? Oh, because if you do not have a number of voters, right, there might be ties, right? Then you will not add this arc, any arc, right? Then it is not semi-complete digraphs, right? Of course, you can construct the gadget. Problem is still equivalent to this known algorithms then. Yeah. Yeah, semi-complete is also hard. Yeah.
I mean, we cannot show
Exactly. We cannot otherwise it's hard, right? If you do not, for even number of voters also the problem is hard, right? But we were doing this reduction because we want to come up with some algorithms, right? And then it becomes directed. Then it becomes a normal directed graph, right? And then what known for normal directed graphs we can still apply, right? But these algorithms are much more faster. Like tournament algorithms are much more faster than known for arbitrary directed graphs. Yeah. Okay. Okay. Thank you.
So we have high tea now till 6, and then we will come back for an interesting lecture by Shushmita, study abroad. So opportunities and other things. So let's come back here by 6. There are snacks and teas outside. See you in some time.